Hi everybody, welcome back to Chem 121. Today we are going to finish up Chapter 5 and have a review. I do see that there aren't a ton of people here yet, so hopefully people will start to filter in before the review so that there will be a selection of questions to go over. If there's not, then we'll just stop the video at the end of the lecture of Chapter 5. Stuff that is important is shown down at the bottom. I just noticed that there is a typo. Let me see here. Well, it's just I just need to put a space there. So quiz number 4 and worksheet number 2 are both closed tonight. Oh, I do have a typo here. So last call for quiz number 4 and lab worksheet number 2 is tonight. There we go. And then the exam is on Friday. If you have sent me an email to request that your exam date be moved to either Thursday, which would be tomorrow, or Saturday, which would be 3 days from now, if you did that before, like, I don't know, 1 or 2 a.m. last night, I've probably already replied to you and said, hey, it's done. If you emailed me after that, I haven't gotten to my email yet today. I will attend to that after classes are done. So you'll get a notification at, like, I don't know, 4:30 or so, or maybe even later tonight. It depends on when I can get to it. I do have something going on after classes today. Okay, yeah, that's really all I have for that. So let's finish off Chapter 5. I do need the tablet. Let me grab that real fast. My cats have immediately come to investigate. Why are you talking, Professor Wes? My cats call me Professor Wes. And I'm like, this is my job. I've sat here and done this for 5 weeks now. And they're like, we can't believe it's week 5. And I can't either, to be honest. When is the midterm open? At 12 a.m. on Friday, and it stays open until 11:59 p.m. So 24-hour period. You can take the exam twice during that period. You can do that whenever you want. So if you're like a night owl like I am, and you want to just get it out of the way, it does open at 12 a.m. You can take it as soon as it opens. If you're a morning person, you can take it as soon as you get up at 6 a.m. or whatever. Something that I believe happens, I'm not 100% certain on this, but I want to say I've heard students tell me this. If you start the exam with not enough time left, like you start past 10 p.m. Before it closes or something. If the assignment closes while you're taking it, it kicks you out of the assignment. So don't be taking the exam at 11:30 because you only have 30 minutes to do it, and that would be bad. So plan ahead. I do not extend your exam for any reason unless you have like serious problems. Like my kid had to go to the hospital would be a good one, and then I make you document it. So you do need to provide paperwork in those instances because it can get audited, and I do need to report that if that does happen. So do the best you can with plans, and 99% of cases you should be all right. All right. On this slide that you see on the screen here, we talked about, there we go. Yesterday we talked about these numbers that we assigned to elements called electronegativity. And we described that an element with a very high electronegativity pulled electrons to itself very strongly. An element with a very low electronegativity did not. And that if we considered the difference in electronegativities, we would determine the properties of a bond. And we said that this should be edited on your version because I edited it yesterday. I did this 0.4 or less. So 0.4 included. We call those nonpolar. The electron density is roughly equal across the bond. The electrons spend equal time by both atoms. If the electronegativity was between 0.4 and 2.0 difference, the bond is polar and the electrons are shifted in one direction over the other. So one atom watches over the electrons more than the other one does. And then if the metal, let me just cross this one out because this is not necessarily true. And we said that yesterday. And then if it's greater than 2, we consider the bond to be ionic because the electron's essentially passed over at that point. So what we're going to do is we're going to look at various bonds, and we're going to represent them with symbology that is appropriate for their polarity. So I have the HF molecule on the screen here. The electrons aren't drawn on. I could do that really quickly, but they aren't really the point of this discussion here. So there's 2 ways that we're going to do this, and I showed you the first one yesterday, which was to write these delta squiggly circle symbols. What this means, just as a refresher, in case you forget, so this right here, the delta is a partial charge, so you can think of it as like 0.5 of a charge, or 0.3, or whatever. So instead of shoving an electron entirely across the bond so that one atom takes the electron and the other one gives it up. Sorry, my cat is meowing at me again. You can probably hear him now. Instead of pushing one electron from one atom to another, they're still shared, but they're more located towards the side with the delta minus. The delta minus being the charge of the electron that is closer to it. The delta plus side is the side where the electron left from temporarily or most of the time, and thus is the partial positive side. So you can either use delta plus or delta minus. We're going to use those a bunch in later chapters when we're drawing pictures of molecules. The other way that we're going to represent this is we're going to draw an arrow like this. We're going to draw an arrow with the plus end on the delta positive side, and we're going to point toward the negative side. All right. I don't have any examples here, so what I'm going to do is I'm going to give you some bonds here. So I'm going to write down, oops. I'm going to just write this down on the screen and have you do this. So I'm going to have this bond. We'll have this bond. And we'll have this bond. That looks good. Now, you do need an electronegativity chart to do this. Now, fortunately, if you go to P-Table and you click on the tabs on the right, I'm going to just paste this into the chat for you. If I do this... So, this is the link that I sent you. It shows the electronegativity, so you have an electronegativity chart here. So I'm going to just kind of make this a little smaller. I'm going to put it right here so that you have these numbers. So what I want you to do is draw the appropriate symbology. And I'll do both, but you can do either. You can either use delta plus, delta minus, or you can use an arrow pointing in the correct direction with a plus at the other end. Okay? I'm going to give you 2 or 3 minutes to try these examples just so you get into the swing of it, because we're going to be using it in just a second, and we'll go over the answers when I get back. So see you in a bit. One more minute, we'll go over the answers here. All right, let's go over the answers here. So I'm going to leave this on the screen while we do this. I'm going to write the electronegativities of all the elements underneath them. So carbon, according to this chart. Now, you'll notice that this chart, the numbers are slightly different than your textbook. That's okay, because we're really just caring about them relative to each other. Which one is bigger and which one is smaller, so that you can put the correct symbol on the right side. In fact, I'm looking at all of these numbers, and they're all different than what I have memorized. It's like I just wrote 2.1 out of habit there. And it's completely possible that they have updated these. Maya, please. Maya, please. Go on. Just sitting here yowling at me. And then sulfur is 2.58. And then what is nitrogen? 3.04. Okay. All right, so there's our electronegativity. So I can get this off the screen now. And so what we're going to do is first I'm going to write delta plus and delta minus, and we'll do that in purple here. So delta plus would go on the side that has the lower electronegativity, so that would be this and that. And we'll do that for all these. So this one is the bigger one, this one is the smaller one. So over here, this is the smaller number, so it's delta plus. This one is the bigger number, it's delta minus. There you go. Is it okay to use the electronegativity from the online table? You can use any table you want. You should get the same result. And then finally, to draw the arrows, we're going to point them in the direction of delta minus. So that would be like this, and this, and that. And there you go. All right, so now that you understand how to draw these polarity arrows, you've seen some examples. We're going to do this with molecules that have multiple bonds in them. So I'm going to clear the screen real quick. So the way that this works is that you first do that process that we just did. You assign electronegativity numbers and then point an arrow toward the more electronegative atom. You do that for each bond in the molecule. And then what you're going to do a process called vector addition. Now, this is something that you would take a physics class to learn. So if you've never taken a physics class, you've probably never heard of vector addition. What vector addition is, it's sort of like if you could program something to move along arrows, what the result would be. So, for example, if I was trying to add these vectors together, so I'm going to program an object to go in this direction, and then I'm going to program it to go in this direction. What would the result be? So if I were to add these together, here's what would happen. Well, first I would carry out this instruction. So if this is where I'm starting, I would go this way. And then I'd stop. And then this is my second instruction. So I would start here and then go like that. And this is where I'd end. So the end result was that I just did this. Okay, this is what vector addition is. It's consider all of the bond polarity arrows that we're about to draw as instructions. And then carry out the instructions. Where do the electrons go along those arrows? In this case, if I had them move to the right and then down, they would have displaced from the start here to the end here. So if this was my molecule, there would be the molecule's polarity. So we can find if an entire molecule is polar or not based on how these electronegativities are distributed throughout a molecule. And if you have a bunch of highly electronegative atoms on one side and a bunch of high electropositive atoms on the other, the electrons are going to shimmy in the direction of the negative ones, right? All right, so let's do some examples here. Now, the results that I'm showing right here will tell us, is the molecule have any polarity at all, or is it polar? If all the arrows are canceled out, that is, when you input all the instructions for the vectors, do you end up back where you started? So if I did something like this, if I input this instruction for step 1, and then I input this instruction for step 2, I would do that, and I'd end up back where I started. And we would call that nonpolar. If you don't end up where you started, then the molecule is polar, and the polarity is going to be in the direction that your start-to-finish arrow is, like I showed you, that diagonal arrow that we just had. So let's look at some examples here. Here's how this works. On the screen, you see CO2. And I have gone and written down the electronegativities. I'm going to write them down from P table here. So carbon is 2.55. And oxygen is 3.44. And over here, it would be 3.44 also. So what I did was I drew electronegativity arrows for each bond. So this first bond between this carbon and oxygen points towards oxygen because oxygen is more electronegative. The second bond over here points towards this oxygen, again, because oxygen is more electronegative. So now what I'm going to do is I'm going to treat each of these bonds as instructions, and I'm going to move my electrons along the arrows. So I'm going to start by doing this action from a starting point, and then I'm going to do this action from where I end up after that starting point. So this will be instruction 1, and this will be 2. And here's how that works. So I flipped the instructions. That's okay. You can do them in any order you want. So here's my first one. I have started right here, and I have moved my electrons to the left along this first bond. But the second bond then comes along and shoves them right back. And that makes sense, right? Because my polarity arrows point in opposite directions. So if the electrons are following those arrows, they're going to follow one and then the other, and then end up where they started, right? Since that happened and my electrons have an overall net distribution of nothing, we call this molecule nonpolar. And it is. CO2, carbon dioxide, is nonpolar. All right, let's look at another example here. So we're going to look at SO3. I've done the same thing for SO3. Sulfur is less electronegative than oxygen, so all the arrows are going to point at the oxygens. And then I have H2O down at the bottom where all the arrows point towards the oxygens because, again, oxygen is more electronegative. Now, I can put these arrows wherever I want to. They just have to be parallel to the bond that they are representing. Now, looking at this first one up here, if I do these 3 instructions in a row, in any order, it doesn't matter, where will the electrons end up? So I'm going to put a dot down, and I'm going to follow instruction 1, and then I'm going to follow instruction 2, and then I'm going to follow instruction 3. What do you notice happened? Where did my electrons end up? Since they ended up back at the start, we would call this one nonpolar, right? All right, let's look at water. I'm going to just number the instructions, and then we'll execute them. So instruction 1, instruction 2. Now that's interesting. We ended up somewhere different, right? So the result was that I had just done this instead. So what that means is that water is polar, and if I were to draw this as the molecule, this would be its polarity. The side with the H's on it would be the partial positive side. The side with the O on it would be partially negative. All right. That's my pen and paper version. What I'm going to do is I'm going to let this animate because I actually had to program this in for a job interview. And they loved this. So there's my result. I ended up back where I started, nonpolar, right? What about this bottom one over here? Well, we already talked about this. You don't end up where you started. You end up some difference away. And so we'd call that polar. So when you're doing polarity, the best way to interpret this is to interpret your polarity arrows as instructions. And then move along the instructions. Number them all, and then just put all the arrows and go in the orientation that you've drawn them. If your bond points up, do your first move to go up. If the next one points right, then go right, and do whatever you need to. Now, the catch here is that you have to draw your Lewis structure correctly. If you draw the Lewis structure with the wrong geometry, which is why we've done all of this geometry stuff in Chapter 5, you get the wrong polarity answer, okay? So be careful. If you drew SO3 like this, at right angles, then what you would end up with is that these two would cancel out on the top, but this one wouldn't. And you'd get the wrong answer, right? So it's now incredibly important for you to draw your molecule with the correct orientation. Because otherwise you get the wrong polarity result. All right. So what I want you to do is I want you to draw ammonia. Draw ammonia to the best of your ability using the correct geometry. And then I want you to tell me if it's polar. And then what we're going to do is I'm going to draw the structure using the correct geometry. We're going to figure out its Vesper and molecular geometries, try and draw it to that template, and see if we can make a conclusion, okay? I'm going to give you 3 or 4 minutes to do this, because you have a lot of steps. So start with the Lewis structure, then figure out the geometry, maybe amend your Lewis structure from there, and then figure out polarity, okay? I'll see you in a second. Let's go for one more minute, and then we'll show the solution. All right, so what we're going to do here, first we got to go over here. And so the first thing I want to do is draw the Lewis structure of NH3. Not like that, though. That's not even a brush tool. All right, and so nitrogen has 5 electrons. There are 3 hydrogens. Each hydrogen gives you 1 electron. So our structure should look something like this. So there's my basic Lewis structure. What I'm going to do is I'm going to then circle the electron groups to figure out its geometry. So there are 4 electron groups. So the VSEPR geometry is tetrahedral. And of those 4 electron groups, one is a pair of non-bonding electrons. So therefore, the geometry, the molecular geometry, would be trigonal pyramidal. So I need to make sure that I am drawing my molecule as trigonal pyramidal as possible. So I'm going to do that. Like that. And then I'm going to try and draw my trigonal pyramid by just doing this. So this is just an illustration of what I am doing here. So that would be the bottom, and then the top of the pyramid would be up here where the electrons are. All right, so there's our pyramid. So you can see that the nitrogen is kind of floating in the center of the pyramid, and the hydrogens are at the corners at the bottom. And then the electron pairs are at the very top. So what that means now is that when we draw our polarity arrows, we're going to point toward the more electronegative atom. Well, the electronegativity of hydrogen is 2. What is it according to P-table? P-table says 2.2. And the nitrogen is 3.04. So we're going to have a bunch of arrows pointing towards nitrogen. And so we'll treat these as instructions. So I'm going to just number them 1, 2, 3. And you can actually see how this works because I have a computer. This is hard for you to necessarily do. But I could just do this. Copy, paste. So here's instruction 1. And then we'll do number 2 here. Copy, paste. Oops, could not do this because the area is empty. Yeah, that's my fault. Copy, paste. And then we'll do the third one. Copy, paste. All right, where did we end up? So if I do my overall, and we'll do that in a different color here. The overall result is that, well, I started here, and I ended here, so this is my overall result. So is the molecule polar or nonpolar? And the answer is, well, I got a result, so it must be polar. And it is. There you go. So that's the entire process. And it revolves around drawing your structure correctly. So be very careful about that. If you drew your ammonia where you just had the hydrogens kind of fanned out in a circle, and then you put the electrons wherever, and it looks trigonal planar even though it's not, you get the wrong answer. So be very careful about that. All right, I hope that was helpful, because now you're going to do a bunch of them on your own. All right, so here are a bunch of Lewis structures, and remember, all I want you to do is tell me polar or nonpolar. The direction isn't super relevant just yet. For the purposes of this class, I just want you to tell me, is it polar or nonpolar? Because that will help us later on. Okay, so try these. I'm going to give you about 6 or so minutes to do this, because there's a lot of structures. And we'll go over the answers together when I get back. How are we all doing? Let me know if you have any questions in the chat. All right, one more minute to finish as many of these as you can, and then we'll go over the answers. All right, let's do some of these examples here. Now, in the interest of time, I'm going to not be as thorough in... Oops, I got to condense all of my my layers here. Why isn't this working? There we go. Merge layers. And then we'll delete this. And then we can go over here. Okay. So again, in the interest of time, I'm going to draw the geometry correctly based on the assumption that you can do that. That said, I will write down what the correct molecular geometry is. So, since the Vesper is just the family, so the molecular geometry is trigonal pyramidal here. And then when we go to the electronegativity table, it says that phosphorus is 2.19 and chlorine is 3.16. So all my arrows are going to point away from phosphorus and towards chlorine. So if I do these as instructions, I would get something that looks like this. So diagonally down, like that. So there's the first one. And then I get something that's kind of like that. There's the second one. And then I get something that's kind of like that for the third one. And so the start and the end point would be this. So that should be your thought process on how you're doing this. Do I get a displacement of electrons? Do they get shoved to one particular end of the molecule? Or do they get shoved around back to the start and they're just where they were? All right, so that's the first one. Then we got CS2. Let's draw that real quick. Oops, my Photoshop will register that I'm clicking on it. All right, so we're going to look at electronegativities. Interestingly, these are extremely close together. And the reason that I put this problem in here is that if you have two atoms whose electronegativity difference is essentially 0.4 or less, remember that we call that nonpolar, right? So we could just not put an arrow for anything that's nonpolar, and we can just immediately go say nonpolar. So that's convenient. But also conveniently, if I did do this, drawing arrows for each bond, you notice that they would just cancel each other out anyway, right? So for that one, we have two ways to get to nonpolar. So if you have atoms that have very similar electronegativities, like sulfur versus carbon, or they're the same atom, such as carbon versus carbon, you don't have to draw an arrow for that because there is no polarity. It's nonpolar, right? All right, we got C2Cl2. So this is what that structure ends up looking like here. And I got to go back to the electronegativity. So I got 2.55 and 3.16. So this bond would be like that. The carbon-carbon bond is nothing because they are the same atom. And this bond would be like that. So let's carry out those instructions. I'm going to start here. I'm going to move in this direction for this first one. And then for the second one, I'm going to move right back. I end up right on the starting point. So this one's nonpolar too. And then finally, the tricky one. CH3Cl is very difficult to conceptualize, but we're going to simplify. And we're going to simplify using electronegativity. So if C is 2.55 and H is 2.20 and Cl is 3.16, these CH bonds are less than 0.4, right? 2.55 minus 2.20 is just 0.35, right? That's less than 0.4. So CH is nonpolar. So we'll ignore it. So the only one that's really left over is this one. And it's unopposed. So that makes that actually rather easy. But what would happen, and we're going to just do this as a little thought experiment here because I have space for it, I might as well. What happens if you do this? What happens if I have a tetrahedron and I have four things connected to it? Where will the polarities go? And I'm going to draw this in here just so you can see that it is a tetrahedron. So there's my tetrahedron. How the heck do my polarity arrows work out? So I'm going to draw my polarity arrows along these bonds. And Cl is the more electronegative, so we're going to point towards it. And I'm going to do the best I can to copy and paste these. Because this is going to look like a mess. So we're just going to... Oops, hold on. We're going to just move them over, and we're going to just steal them. So here's the first one. So otherwise I got to play with layer bullshit, and that's dumb. There's the second one. We're just going to connect them start to finish, like that. There's the third one. And it's not going to turn out as good as I had hoped here. Because the intent is if I had done this correctly, it should have ended up back at the start. It didn't actually do this in my diagram, but I'm going to just cheat and be like, oh, look at that. It ended up back at the start. Because I didn't draw one of the legs long enough, I guess. But the point is that if all four atoms around a tetrahedron are identical, then the result is nonpolar. So some examples of that would be CH4, CCl4, etc. If they're not identical, like in the case up above here, this one right there, then 99.9% of the time they're going to be polar. Now note that this is for if you have 4 atoms around a tetrahedron. If you're not a tetrahedron, the rules might not apply. So if you're ever trying to draw out a tetrahedron, and you can see that this is kind of difficult to get it so that all of the arrows end up where they are, because you'd have to make these bonds over here exactly the right length based on their dimensions. So, for example, this bond going backwards is too long, and this bond coming to the side is too short. I got close enough, though. I tried. All right, I believe that just leaves naming, which we're going to do after the break. There's the homework practice. There's a lot of practice here, so... Polarity is going to be one of those topics that it's like, man, this kind of sucks. I don't know how I feel about this. And then you're going to see it forever. You're going to see this in biology a lot, because it's going to come up in intermolecular forces all the time. So make sure you understand it to a conceptual level, so that when we get to Chapter 7 and we're going to use it again, it's not a huge deal. All right, when we come back from the break, we're going to quickly learn how to name covalent compounds. It shouldn't take more than like 20 minutes. And then I'll open up for review questions. If you have review questions, go ahead and post them in the chat during the break here, so that I have them handy, okay? All right. Let me just start this. We'll get the music going, and I'll see you guys in just a little bit. I didn't unmute myself. Sorry. I'm back. Hello. I'm sitting here talking to the screen and like, why isn't the little bar moving? I didn't hit the button. That's why. There are a lot of buttons in my life, and I don't hit any of them on like Canvas or this program that I need to. I mean, you could reduce life to a series of just like doing the thing, I guess. Like if I push this button, boop, everything disappears, right? And if I push, where's this button? There we go. So we could just enjoy the science and the silence and the solitude. Or I can just bring us back. So like, I just hit all the wrong buttons all the time. That's all. We're gonna do the last bit of chapter 5, which is naming compounds, particularly covalent ones. And I'm gonna put the rule on the board here. We're just gonna skip those first few. Wait, hold on. Why do my slides not have rules? Also, why are all the slides blank? Oh, there we go. This is dumb. I don't know why my slides are... I have the old version of my slides. I don't know where the new version went. That's okay. I'm going to write it out then. Ignore virtually everything on this slide because we don't care about this. So I'm going to scribble out this because this is way more detailed than you need to worry about. But what I'm going to do is I'm going to go over... I got to clear this out of the way. Yeah, this is fine. We don't need this on the screen. So I had these nice little boxes when we did name ionic compounds, and for some reason they aren't in this section. So we're going to name the first element. And we're going to name the second element with "ide" in it. Now, specifically, this is for covalent compounds. And you might notice, wow, this is awful similar. Yeah, but we're going to change it just slightly. And then this right here in the middle is a space. All right, what are these number symbols for? The number symbols are numeric prefixes. And these are for however many of the atom you have. And so this would be like 1 is mono, 2 is di, 3 is tri, 4 is tetra, and so on. And these are all in your book, but I'll write them all out here. There you go. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa. These all sound like shapes after a while, right? 7 is hepta, 8 is octa, 9 is nona, and then 10 is deca. So what you're going to do is for however many of the first element you have, you're going to put the appropriate prefix in front of that and then say its name. So if you have 3 carbons, you're going to say tricarbon. If you had 10 carbons, you'd say decacarbon. And then you're going to do the same thing for the second element with "ide" at the end. So if you had 5 chlorines in your molecule and it was the second element, you would say pentachloride. Now, there are some exceptions that we have to these numeric prefixes. If there is only one of the first element, you skip mono. So we don't say, for example, for CO2, we don't say mono carbon dioxide. That's not what we do. We just say carbon dioxide. So if there's only one of the first element, just say the element by itself. Mono is only used if it's the second element. And then the next thing that we care about is that if you see this combination of letters, then you're going to drop the first vowel. So the A would drop out, or this O would drop out. So this would be something like monoxide, for example. We get rid of this first vowel, and it becomes monoxide. Or, for example, pentaoxide. This is not a vowel combination. It makes too many syllables. So we get rid of the first vowel, and it becomes pentoxide. So that is just a naming convention that makes it sound better, I suppose. Chemists decided upon doing this. So what you want to make sure that you are careful about is when you're typing this into Canvas that you don't make too many typos. So if you type in pentaoxide versus pentoxide, it's going to count that as a typo. And I believe that for the spelling questions, you get either 1 or 0 typos. It depends on the name. So if you make too many spelling mistakes, it counts it wrong. All right. The last thing that I want to mention is that you're never going to use Roman numerals in these because these do not have charges, right? So therefore, no Roman numerals at all. So let's go ahead and do some practice examples of these. So I want you to type the name of what this is in the chat. I'm going to hit mute, and I'm going to give you a second to do that. All right, just a second more, and then we'll go over the answer. Okay. So we're going to name the first element. But we're going to put a numeric prefix in front of it for how many there are. So 2 was di, so I'd call this dinitrogen. And 5 was penta, so we'd say pentaoxide. But AO, we would omit the O, the A, sorry, pentoxide. And so that's what we'd call it. All right, how about this one? Same thing, go ahead. Oh, you already know this, we just did this example. How about this one? Hint, you can't call it water. That's not what it is, right? What's the actual name of this? And then we're going to do a little joke about it. So type in the formal name in the chat. Are we still in lowercase? Yes, all of these are lowercase. Because remember, element names are not proper nouns. Even the ones named after people. Nothing is capitalized in naming. The only thing that gets capitalized with regards to elements is their symbol. All right, we got the answer. Somebody's got the answer. Very good. Oh, 2 people, actually. Or, sorry, just 1 person. So, dihydrogen monoxide. Very good. You may have heard of dihydrogen monoxide as just sort of a joke. Like, people will refer to water as dihydrogen monoxide, just kind of jokingly. Now, interestingly enough, dihydrogen monoxide is kind of a running gag for people that have poor chemical literacy skills. And so I'm going to give you... This is actually all information from a website that is supposed to be a practical joke. But it's written in a very specific way. And the topic is the petition of banning this dangerous chemical, dihydrogen monoxide. So this slide is entirely a joke. This is not relevant to your exam, but I do want to go over it because it highlights the importance of context in chemical literacy. So if you did not know that dihydrogen monoxide was what it was, and you were faced with these facts, you might be concerned. And a lot of people were, and we're going to talk about that in a second too. So dihydrogen monoxide has many, many, many names. One of those names is hydroxyl acid, and it is the major component of acid rain. Did you know that? In fact, like 99.9% of acid rain, dihydrogen monoxide. It's a greenhouse gas. CO2 is a greenhouse gas. Methane is a worse greenhouse gas. But you know what the worst greenhouse gas of all is? Dihydrogen monoxide. Bet you didn't know. It can cause severe burns. And if you breathe it, you will die. That's kind of terrible. And this stuff is all around us. It causes erosion. It corrodes metal. It can cause your brakes on your vehicle to fail. It can cause your electrical stuff to short out. It can cause all sorts of things. Every single person who's died of cancer has had this in their body. It's terrible. And despite all of this trouble, despite everything that we know about dihydrogen monoxide, it's still used in industry as solvent, as a coolant. It's used in nuclear power. It's used to make styrofoam. It's used as a fire retardant and in cruel animal research. It's used to distribute pesticides. You can wash it in your produce all you want, but it's still there. You can't get rid of it. And it's used in junk food. It's everywhere. It's everywhere. And do you know why it's everywhere? Because it's fucking water, right? So if my impassioned speech and delivering of all of these terrible, terrible facts didn't convince you to ban this terrible, terrible compound, the fact that it's just water should tell you that, yeah, this is all a scam, right? So 2 cases where this came up. The first case was in Australia. The other case was in the southern U.S. I'll let you guess which one was which. Case number 1, a Senate hearing for whatever body of government was done in the correct location that this belongs to, proposed on April 1st to ban dihydrogen monoxide, and all the senators voted on the proposal and then laughed at it, and then later on said that this is actually a presentation about chemical awareness and literacy, and that it was important to fund education. So you immediately know this was the Australian one, right? The second case was a radio station on April 1st who said, yeah, have you heard about this chemical compound called dihydrogen monoxide? And they had tens of thousands of people call into the radio station after they listed some of these facts for them in a mass panic, and the radio station was taken off the air and the people were basically fined. I think like they were suspended for several days. I want to say you can look up the article. I believe it was Florida, because of course it was, right? Fucking Florida. But yeah, the important thing here is that all of these chemicals are going to sound really chemically, and the reason that we teach you all this nomenclature is so that you don't fall into that sinkhole. All right, I'm going to give you about 5 minutes to try and name these compounds. Turning the names back into formulas is also important, so make sure you do those too at the bottom, and then there's the homework practice. So I'll check back in 5 minutes, and we'll go over the answers, and then we'll do the review session, which looks like right now is just do this speed of light conversion, which I will happily do. So I'll see you in 5 minutes. One more minute, we'll go over the answers here. All right, let's go over the answers here. Where'd my pen go? There it is. All right, so I got 2 nitrogens, dinitrogen. And I have 1 oxygen, which would be monoxide. Then we got 2 chlorines, which is dichlorine. Trioxide for 3 oxygen. Then we got sulfur. Hexa for 6, fluoride. Now you might look at that and be like, how the heck do you get 6 things around a central atom? Turns out that there are exceptions to the octet rule that we don't really go over in this class, so you might see numbers larger than 4. For something like this, you actually have like a lattice or a sort of chain going on. So this is a more complex molecule. There is no central atom in this, but tetra for 4, phosphorus. And then 10 is deca oxide. Decoxide. All right, down here, write the formula for the following. Diboron, which is B2. Trioxide, which would be O3. Well, then we got carbon disulfide and oxygen difluoride. So, pretty straightforward. We can do that. Really, the trick is going to be the spelling and not making too many typos. So, have a periodic table handy and just be very certain of what you type in. I cannot go back and award points for typographical errors. So if you make a typo and it gets marked wrong, I can't help you, unfortunately, there. All right. That's it for Chapter 5, I believe. There should be, like, a happy dancing orc and music. Yay, there we go. That is such an old picture. I don't even play World of Warcraft anymore. I need to update that. All right, so that's the end of Chapter 5. So the Chapter 5 quiz is already available online. You've now seen all the content, so you can go ahead and take that whenever you want to. With regards to that quiz, I have specifically set it up such that if you take that quiz, it will immediately show you the answers and your score. So that is designed to help you study. So please use that however you find it helpful. We're now going to go over to this, and we're going to do these questions that are in the chat over here that I can see. So I'm going to start up here. So we have the speed of light, which is 3 times 10 to the 8, 3.0 times 10 to the 8 meters per second. Sorry, there's cat hair on my monitor right where I wrote this. And I want to convert this from meters per second to miles per year. So if I have something that's in meters and I wanted to convert it into, well, so first of all, meters per second, and I wanted to convert it from that to miles per year, I have to convert each of my units individually, right? So meters could turn into anything, for example, kilometers, and then I can turn that into miles because I know how to convert those two. I can look that up online. But seconds to years is a little bit more tricky because I have a lot more steps. So I can turn seconds into minutes. I know how many seconds are in a minute. I can turn that into hours. I can then turn that into days because I know how many hours are in a day. And I know how many days are in a year. So my plan is to do something like this. So if I can turn meters into kilometers, and then turn kilometers into miles. Oops, that's not where I wanted to put that. What am I doing? Can't write and speak at the same time, sorry. Then I would have this part done because I would have an answer in miles per something, right? So let's go fill in the numbers. 1 kilometer is 1,000 meters, right? And then how many miles per kilometer? We can look that up on Google or look in the conversion table. And Google says that in 1 mile there are 1.609 kilometers. All right, so I've taken care of the miles unit. The miles unit is good to go. We can just leave that here. I had to deal with the seconds unit, though. So I have seconds over there. In order to cancel it, I have to put it on the opposite side of the bar because anything on the opposite sides of the division bar would cancel, yeah? We're going to turn seconds into something else. We'll turn it into minutes. We'll turn... Oh, goodness. We'll turn minutes into hours. So we're just working our way along this sort of path that we've constructed down here. So this is the unit blueprint or the unit map that I talked about earlier. We'll turn hours into days, and then I got to start down here. And then we have the units that we want. So this would be miles per year. And so now I just got to go fill in the numbers. So 60 seconds per minute, 60 minutes in an hour, 24 hours in a day. And then how many days are in a year? Well, if we worry about leap year, it's best to just look this up and then use this number. So 365 and a quarter days in a year. And then you just punch all of this into a calculator. And when I do this, I get 5.9 times, what was my answer? Times 10 to the 12. And the circled units, the ones that are in blue, are the only ones that are left over, so that's my answer. And then finally, you just check for sig figs. This only has 2 sig figs, so that's going to affect our answer. All of so exact. These are all exact. And then this one is 4. And this one is 5. Well, my S didn't show up. There we go. So if you can do that conversion, you can do any conversion, I think. Really, the trick is just line up the units and then put in the conversions. All right. The next problem that we have is this motorcycle problem. Which I guess I could just highlight these. Does it stay highlighted if I do that? No, now it's just impossible to read. Okay, well, it's this one that we're going to do. All right, so I've got a motorcycle. So here's my motorcycle here. It's got like a seat and handles and an engine and an exhaust pipe. There we go. So we're going to drive all the way to Seattle. So Seattle is basically the Space Needle and a bunch of tall buildings, right? And that's it. And it takes 25.1 minutes to cover this distance. And the speed is 57.5 miles per hour. This pen, I swear. It's not the pen, it's Photoshop. And so what we want to do is we want to figure out the distance that the motorcycle traveled in centimeters. Okay. Well, if I have a time and I multiply that by distance over time, the times would cancel out, right? And I would get distance. Provided that the times are in the right units. So I have time here that I can work with. However, it's not in the right units to let them cancel out. Because if I multiply something by minutes, or something with minutes by something in miles per hour, I get the wrong unit. So what I need to do is I need to turn this one into hours. So let's do that. And then we'll punch it in our calculator. So 25.1 divided by 60 is 0.418 hours. So we were driving for about 0.418 hours. Okay. Now, if I take this number and I multiply it by this number, what will happen? Well, in 1 hour, I would go 57.5 miles, right? So in roughly half of that time, how far would I go? Well, I just multiply these two together. And I get 24.1 miles. So that's the distance that I traveled. So we have learned that this distance up here is 24.1 miles. Now, the problem wants you to know what the distance is in centimeters, so you need to convert... Oops, I need to mute that. You need to convert this distance from miles to centimeters. Well, we can do that. And there's multiple ways to do this. You can turn miles into kilometers, then kilometers into meters, and meters into centimeters. And once you've filled in all the numbers, that should be the distance in centimeters. So let's go fill in all these numbers. So there's this many kilometers in a mile, 1.609. A kilometer is 1,000 meters. A centimeter is 10 to the minus 2 meters. And then we can just multiply. 24.1, 609. And when I do all of that, I get 3877690, which would be 3.88 times 10 to the 6 centimeters. And then how many sig figs should our answer have? Well, all these numbers that we've been using all along. So this had 3 sig figs, so this should have 3 sig figs. Which means this has 3 sig figs. Which means that has 3 sig figs, because that's the lowest that we had the entire time. All right, hopefully that's helpful. Let me know if you have any questions about that. Then we'll do the last one that's on here, which is The current market cost of pure metal, $5.69 per kilogram. What volume costs 182? Here's the density. Okay. So you know that the density for this particular metal is 11.9 grams per cubic centimeter. And you also know that the cost is $5.69 per kilogram. And you are given $182, and you want to find the volume. So what you need to do is you're starting with money here. Let's not write that over there, actually. So you're starting with money, and you need to turn that into something. Well, you have a relationship right here. You could figure out how many kilograms that money would buy you, right? It's $5.69 per kilogram. You have $182. Once you know the mass, which is this, you can use the mass to figure out the volume using the density, but the units don't match, so you got to do that first too. And then you can convert to cubic centimeters once you're done. So you follow the logic of the units. I can turn money into a mass, which I can then turn into a volume. So let's do that. So I have a certain number of dollars per kilogram. The dollars would cancel, except I can't draw them. There you go. And so that's what, $5.69 per kilogram. We'll turn kilograms into grams. A kilogram is 1,000 grams again. And then we'll turn grams into cubic centimeters. 11.9 grams per 1 cubic centimeter. And you're all set. So now we just have to do the calculation. That's not my calculator, that's my phone. So 182 times 1,000 divided by 569 times 11.9. And the answer I got to 3 sig figs, because that's what everything is here, is 2,690 cubic centimeters. All right, it's kind of a tiny review, but I hope that was helpful. So seeing more of these problems done, really the best way to be successful at this stuff is to do as many of these as you can. Because you're going to see them on the exam, and then you'll see them again on the final. And you'll even see them again next week when we start Chapter 6, which is we're doing this stuff again. We're going back to it. It's not on exam number 1 because it's Unit 6, so you don't have to worry about it now. But the first thing that we're going to do next week is we're going to do unit conversion and dimensional analysis all over again. Using new units that relate chemical concepts. So we're going to talk about the mole and how many grams there are per mole, and we're going to do chemistry that way. And by the end of that, you're going to be able to answer, okay, if I have a 250 milligram tablet of Tylenol, how many of those milligrams are carbon, and how many of them are hydrogen, and so on and so forth. You'll be able to do that. All right. Normally what I would do is I would open for questions, but we only have 5 minutes left, so I'm going to call it a day here. You are free to ask me any questions that you would like over Discord or by email, and I will get to those as soon as I'm able to. I want to thank everybody for coming out to the lecture and to the little review that we had at the end there. Exam number 1 is on Friday, and there is some stuff that is due tonight. Quiz number 4 is due tonight. Lab worksheet number 2 is... It's not that they're due, they close tonight. So get those in by the end of the evening, and then do the Chapter 5 quiz for a little bit of practice before the exam, and you should be all set. Remember, the exam is on Friday. It is open for 24 hours. Make sure you email me if you need the date changed to Saturday or Thursday. Have a good one, take care, and good luck. We're all counting on you.